In this Let's Take a Moment, I want to talk about the Earth's internal layers. We learned in our last Let's Take a Moment that we can use seismic waves and their velocities to determine the different layers inside the Earth. So let's now define those layers. Now I know you've looked at that, hopefully both in the reading and in the PowerPoint, but I want to just talk about this for a minute because this is really important. So let's start on the outside of the Earth, right, where we live, and let's work our way inside. So the first layer that we would come to is our crust. Now our crust comes in two types. We can have continental crust, and hopefully you're already thinking about where you would find that, and we can find oceanic crust. Hopefully it's pretty easy to figure out where those are. Now, let's think about our thicknesses here of both of these crusts. Our continental crust is thick because it is above sea level, right? Except everywhere but New Orleans, right, where we live, but everywhere else, right, it's much thicker. Our ocean crust, however, is very thin. So if we were to depict it, it might look something like this, right? Where our continental crust is over here, and our ocean crust is over here, much thinner. Now, I do want to mention this here because this can be really confusing. Even though our continental crust is thicker, it is really light as far as its density goes, because it is made of mostly felsic material. So there's that tie back to our first Let's Take a Moment of this chapter. So remember, felsic material contains a lot of silica and oxygen. So if it has a lot of silica and oxygen, it's going to be really physically very light. So don't get that backwards. Even though the continental crust is thicker, it's much lighter than our ocean crust. So our ocean crust is very heavy. And if you think about it, that also makes sense because our ocean crust sits below sea level. It's sunken, right? It's not at the same level as our continent. So, and it's because mainly our ocean crust is made out of mafic material. So we can even add that here. Our continental is felsic, and our ocean is mafic. Alright, so again, if we were to take a look here, as we would see, our continental crust is really thick, and our ocean crust is pretty thin. Now, this dividing line here, right there, between our crust and our next lower level, which is going to be our mantle, remember, we're going to call that the moho. So let's talk about the moho here for a minute. Let me erase this good stuff here. So if we talk about the moho, in your book it's defined as the Morohovic discontinuity. We call it the moho for short. What we're going to see here that tells us the differences between the upper crust and everything down below is going to be a velocity change. Now, what we're going to see is that the velocity speeds up as it crosses the moho. So since it speeds up, that shows us there's a layer difference there. Right? So that's why we define that there. Now let's talk about our next layers here, down below. So down below our crust is going to be our mantle. Now we can divide our mantle into two different layers, the upper layer and the lower layer. The upper layer up here is not going to be very thick, but it's right underneath our crust. Okay. Our lower mantle is definitely really thick. Okay, so let's see, here we have the crust, here we have the upper mantle, and here we have the lower mantle. Now our upper mantle, what's really important about it is that it is solid. That is really important. So it is solid and it connects to the crust. So when we talk about a plate and plate tectonics, we're talking about those two layers combined. We're going to give that a name here in a few minutes. But it's really important to recognize that the upper mantle is solid and immobile, right? It's not liquid. Our lower, however, is what we call partially molten. I like to think of the lower level of the mantle like a slushy. If you think of a slushy, right now I might be making some of you thirsty, but if you think about a slushy, you have liquid in there and you have ice. That's like the lower mantle. We have solid and liquid both in there. Now what we're going to see in our next chapters is the lower mantle is going to become really important because since it's partially molten, it can move. So the lower mantle can do what we call convect. And you've all seen convection before. Convection is like a lava lamp. If you think about a lava lamp, right, the heat source is going to be the light bulb. So if we compare that to the earth, the heat source is going to be the core. So if you think of your lava lamp, that lava that sits by the light bulb, as it gets heated up, what happens is as material gets hot, it gets less dense. So when it gets less dense, it's going to rise. You might have experienced this too if you live in a house that has 2 levels. All the hot air is always up at the top. Now, as that lava in the lava lamp sits up at the top of the lamp for a while and gets cold, it's going to become more dense. Anything that's cold becomes more dense. So what does it do? It sinks. So our lower mantle does the same thing. This area down here is close to the core, so it's getting heated up. So what's going to happen is that material is going to become less dense and it's going to rise. Now, as it sits up at top for a while and cools down, it's going to become more dense and it's going to sink. This interaction is going to be really important when we start to talk about plate tectonics. So keep that in mind because we're going to revisit this idea later on. Now let's talk about our core. Our core also has 2 layers. We have the outer layer and we have the inner. The outer core is going to be pure liquid. And again, we know this by looking at seismic studies. So I failed to mention that here a few minutes ago, but remember we defined that boundary, the MOHO, by our velocity change. We also see a same velocity change right here between the upper and lower mantle. Now, if we think about it, we know that the Earth gets more dense as we go interior. However, since the lower mantle is liquid, what we see is the velocity of our waves slows down. Okay? Right here, we call this the low velocity zone. Now, we're going to see the same thing between the lower mantle and the outer core. Right here at that boundary, our waves slow way down. We actually call that the ultra low velocity zone, right? So the ultra low velocity zone, right, is telling us that our waves slow way down because it is a liquid. So since it's a liquid, it's naturally low dense, okay? Now, our outer core is liquid, and as we learned, the convection also occurs in the outer core. Now, the inner core, however, is solid. Okay, so the inner core is solid. And what we see is this convection from the outer core to the inner core, on top of that inner core, is what makes our magnetic sphere around the Earth. Right? So that's what gives us the aurora borealis that we also talked about earlier in the chapter. Now, our inner layer is solid, and what we think is that it's probably very mafic. Now, what we actually use is actually probably ultramafic. As we also look at meteorites. Meteorites can give us a really good idea of some of these lower levels of the Earth. Now, we can also look at the velocity change there between the outer core and the inner core, and what we see is right here at that junction, the velocity speeds way up. So that tells us that our inner core is extremely solid and very, very dense. And it's really mainly solid, even though there's high temperatures in there, it's mainly solid because of all the pressure, right? So if you think about it, that inner core has all the pressure of the entire Earth sitting on top of it. So all that pressure is going to make it stay nice and solid. Now, there's one more thing that we can add here. 2 more designations. The core and the upper mantle is what we call the lithosphere. So when we would talk about a plate and plate tectonics, we're talking about the lithosphere. So remember, this is rigid, it's solid, okay, there's no liquid, okay, as far as those rocks go. Now, our lower mantle just by itself, this is what we call the asthenosphere. So, remember, the asthenosphere is partially molten. And it's really the interaction between the lithosphere and the asthenosphere, between these two layers, that define all of geology, that define all of plate tectonics. And that's mainly what we're going to talk about in our next two chapters. So I hope reviewing these different layers inside the Earth really helped you understand what's going on inside the Earth, how we know it's there, how we've defined it, and how each layer is different.